Okay, here's part 3 of the opening lectures on Faraday's law. Specifically, this has to do with the fourth problem in the lecture examples in the folder for today. As we'll see with this fourth example, when we get to the last portion of it, there's something a little bit more fundamentally going on here. Okay, so here is the problem. We have a circular loop of wire. It has a radius of 0.1 meter. Like so. Okay, and then we have a magnetic field that is present. The magnetic field is perpendicular to the loop and it increases with time at a rate of 0.1 Tesla per second. So we're going to write this as a dB dt of 0.1 Tesla per second. Okay, then in part A of the problem, the resistance in the wire is 1 ohm. Find the induced current. Okay, so now in this example, as opposed to the last one where we changed the area of the loop, in this one we're changing the magnetic field. So let's kind of begin in the following way. Okay, let me go ahead and say draw 2 field lines to begin with that are coming out of the board like so, and then time goes by. We then end up with the same loop as before, but now instead of 2 field lines coming out of the board, let's say that instead we have 4 of them. Like so, and the reason why is because the magnetic field here, its magnitude is changing with respect to time, it's increasing. Okay, now the induced current has to flow to oppose this. So if we've got more and more B field lines coming out of the board, then the induced current has to flow like this to give us its own magnetic field into the board to compensate. So therefore we end up with the induced current flowing here clockwise on the diagram. Okay, now let's go ahead and write down our flux integral here. So phi is going to be B times A. It's going to be B times pi r squared. Okay, let's go ahead and get the directions here correct. So for example, if I've got the B field coming out of the board and I have the induced current flowing like so, this gives me an area vector into the board. There's a 180-degree angle between B and capital A. Cosine of 180 is equal to -1. So then therefore this flux has to be written as a negative number for that reason. Okay, now we'll go ahead and take its derivative with respect to time. When we do differentiate with respect to time, what is changing with respect to time here is the B field. So then therefore we'll write this like so. The area of the loop remains constant. Okay, and then we'll take the negative of this and place that then into the right-hand side of Faraday's law. So in the right-hand side of Faraday's law, let me go ahead and write the expression first. The negative signs will then therefore cancel. And we end up with this. Okay, the left-hand side of the expression, the induced EMF from Ohm's law is just I times capital R, where capital R, the resistance, is just 1 ohm. So let's go ahead and now calculate the current I. That will then mathematically just finish the problem for us. But for now, we've got, let's see, 0.1 Tesla per second times pi times the radius squared, so times 0.1 meters squared, like so. And this then gives us 0.003, and then we're calculating current here by dividing by the resistance of 1 ohm. This then, of course, is in terms of amperes. So a basic problem similar to the other examples that we looked at. But as I said, there's something a little bit more fundamentally going on here, and that's what's being described in part B of the problem. It says, find the induced electric field. So what's being asked for here? Well, we've got a conducting wire and a current is flowing. So then therefore, if a current is flowing, what has to be present within the conducting wire if we go as far back, for example, as say chapter 25, an electric field. So an electric field is present inside the wire. More fundamentally, what's going on here is that when you have a changing magnetic flux, it doesn't induce a current. It doesn't induce an EMF per se. Those are descriptions of what happens in electric circuits. A little bit more fundamentally, what happens is that it induces an electric field. A changing magnetic flux induces an electric field. So we initially described Faraday's law to you with demonstrations involving solenoids and bar magnets and wires and voltages and so on and so forth, because it's relatively easy to see and you can see it happen in front of you with a simple demonstration. But a little bit more fundamentally, what's happening is that within the wire itself, you end up with a circulating electric field. So then therefore, I'm now going to replace the wire with that circulating electric field in the following way. All right, so now think of the loop that I've drawn here, the blue circle, as not a wire, but instead it's now an induced electric field that circulates on this diagram in the following way. Like so. Specifically, what's being described here on this diagram is a line integral. The line integral is written in the following way. This expression right here. This expression right here is a closed path integral circulating, in this case, on my diagram like so. What this literally means is that if I take a bar magnet, for example, and I point it at you like this, so you're seeing these B field lines, and then I do this, such that right here in this region of space, I've changed the magnetic flux. What I actually induce in this region of space is a circulating electric field. This is starting to lead us towards the propagation of what is referred to as electromagnetic radiation. We'll get to that, however, a little bit later on as we complete here the last portion of the AP curriculum over these last couple of weeks prior to the AP exam itself. But when you have a changing magnetic flux in a region of space, that then induces an electric field. This expression right here replaces the EMF, if you will, in the left-hand side of Faraday's law as you saw it earlier. Here's then how we write Faraday's law. Like so, where on the right-hand side of the expression, let's go ahead and put in the flux integral for magnetism. And write the expression like this. Like so. This is a more formal way of writing Faraday's law. When you have a changing magnetic flux, that then induces an electric field. Okay, now we have seen this expression here before. Here's how we saw it back in chapter 23. A potential difference, let me just write it as delta V. We saw that potential difference as the right-hand side of the expression like so, when setting up calculations involving calculations of difference in electric potential. Recall that in some of those problems that we did in chapter 23, we were messing around essentially with the right-hand side of the expression. Notice that I've written essentially the right-hand side of the expression here on the left-hand side of Faraday's law. But there are immediately some differences in the expressions. Take a look at the closed symbol. The closed symbol means that we start and stop in the same position in our path integral on the diagram. What's that equal to here, however, back in chapter 23? Well, if you start and stop in the same position on the diagram, the potential difference between those 2 points should be 0, right? Well, it is back in chapter 23 when you're talking about, for example, an electrostatic situation. Not so here, however, with Faraday's law. With Faraday's law, even though you start and stop in the same position, there is an EMF that is still present. Once again, this is fundamental to nature. So how do you kind of grapple with this in terms of conservation of energy? Here's the easiest way of thinking of it. Back in chapter 23, when talking about electric circuits, for example, or actually before that, back in chapter 23, that is when talking about electrostatic situations, well, basically everything was just sitting there, and all that we were calculating were basically differences in potential energy from one point to the other, and then just dividing out by the test charge. That's basically what that expression is describing. That's a conservative situation where you have, for example, what happens then when a proton, say, falls downhill from high potential to low potential, and potential energy is transformed into kinetic energy. Not so here. This is a non-conservative situation. So where is the energy coming from that is causing all of this? It's coming from me when I do this I am supplying a non-conservative force such that I induce an electric field here in this region of space. Okay, now it does say in the problem to find the induced electric field, so let's just go ahead and calculate it here. In order to do so, we'll now go ahead and set up this expression. All right, so the EMF that we found earlier, I times R, I'm now going to write as the left-hand side of Faraday's law, like so. Okay, now the only line integral, the only path integral that we have to worry about here with this topic is the circle that I've been describing throughout this problem. So then therefore this expression here is equal to the electric field multiplied by the radius of the circle, the radius of the loop of wire in the actual example. So then therefore the electric field itself is I times R and then divided by 2 pi r. Okay, whatever that number is, I forgot what the numbers are in this problem. I've erased them. We can just go ahead and calculate that out. And when we do, we end up with an electric field. It's usually written in terms of volts per meter. You could write it, if you wish, in terms of newtons per coulomb, which is the same thing. But usually in this context, we write it out as volts per meter. Okay? Okay, that concludes part 3 of these opening lectures here on Faraday's law. Okay, next time I'm going to start to go through applications of Faraday's law, generators and transformers, and then we'll begin to work our way forwards as we begin to approach the end of the AP Physics C curriculum. Today's t-shirt was Black Sabbath. Everybody stay safe. Remember, we're all trying to crush the curve.